Now we will come to the next class of binary stars, the astrometric binaries. You might have seen in the visual binaries, if you have seen that video before, that you are able to resolve the two bodies spatially. You can see both of them together. In astrometric binaries, it is not always the case. It is possible perhaps that you can see them together, but at the same time, it may happen that you are unable to resolve both the objects. You might be following only one particular object. Okay? So, what you see as the rotation of the big star around the center of mass, and I am saying big star because we saw in the mass luminosity relation that a more massive star is bigger in size and has greater luminosity. So, if you are unable to resolve two sources, then the one source that appears to you is the bigger star, the more massive star. Okay? So, now what happens is that you are able to locate one star. When I say locate, it is a function of time. You are able to measure the position of the star, and if one star is very massive compared to the companion star, then what happens is, we saw in the previous videos on the visual binaries where we looked at the different orbits, we saw that instead of a rotation, very often you see a wobbling effect of the more massive star, because it is rotating about a center of mass which is very much inside the body itself. So, the point of rotation, the reference point of rotation, is not outside the body but inside the body, and hence it results in a wobble. So, when you are able to see the wobble, and at the same time, if you can see the proper motion of the stars, then you can measure the parameters of the star which are needed to get the parameters of the companion star. Okay? So, these stars where you measure the location, the wobble or the rotation, maybe of both the stars or maybe of one star, and you follow the proper motion, and what you ultimately get is a combination of the two, that requires very precise astrometric measurements. And that is when we call these binary star systems as astrometric binaries. So, now Sirius is another very good example where good astrometric measurements have been made. And Sirius is one of those objects where the measurements have actually proved to be kind of a foundation for development of the whole methodology of observing binary stars. And of course, Procyon is another such object. If you have gone through the video on the introduction of binary stars, where we had mentioned what Bessel had written to Humboldt, that he inferred Sirius and Procyon to be binary stars, although they were unable to see the companion stars at that point of time. Okay, subsequently they were resolved and observed using telescopes, but Bessel had predicted, and it was seen later and observed later. So this is one such example of a binary star system which you see out here. You can see I hope this green square is visible to you. Okay. If not, then perhaps you can take a snapshot of this video and expand it, and hope it will be visible to you. But this is one such a system where you can see a astrometric binary at work. Now, these are examples of astrometric binary. So we are looking at Procyon. This is your Procyon, and you can see Procyon B has an orbit like this. Okay, to see Procyon B, we have to reduce the threshold of observation for Procyon A, and hence this object appears so blurred and huge. Okay, now if you just remove this object out here and take the center of mass of the system, then you can see that this is the center of mass of the system, and this is the orbit of Procyon B, very precisely measured. Okay, this requires actually the cutting day observational technologies to measure these with this accuracy, the binary parameters. So although when we talk about binary star systems, we talk about Galileo and Herschel and Bessel in the 19th centuries and all, they were the pioneers. But today also, the observation of these binary star systems is cutting edge research, because we are getting deeper and deeper insights as we get into the more precise observation of these systems. Okay, now we were talking about astrometry. So understand that when we mentioned this elliptical motion and the proper motion, then what we see on the sky is a sum of the two. Basically, sum of the binary motion around each other, and this whole binary motion, the whole binary system is moving in the sky because of the initial kick velocity that it had received. Okay, so what you actually see in the sky is something like this. Your Sirius A moves like this, and Sirius B is moving like this. Okay, and mind you, these are very, very accurate observations, and just look at the time scale at which we are observing. This was the position in 1910, and this is where you see in 1990. So it requires generations of astronomers who are passionate about understanding the universe and continue with the observation, knowing very well that perhaps the observation that I do today, I will not be able to understand or get a full picture. It will be someone in the future who will get a picture out of it, who will create a better, complete picture. Of course, there's nothing like completely complete. Whatever we understand is obviously an incomplete compared to what the future generation will understand. And this is how research works. This is how civilizations work. And this is how astronomy has been the oldest science. Now coming back to the dynamics of the system. So this is the elliptical dynamics of alpha CMA. Okay, and you can see that we have observations around 2000, 2002, 2004. Okay, these are the observations which were made, and from these observations it is predicted, because this observation was made something around 2008, 2010. Okay, so observations were made of these points were actually measured points, and these points are predicted points. And given the efficacy of Newtonian dynamics, which has been proved to be correct, of course, with the correction of general relativity, but in many cases, Newtonian dynamics is enough, because the correction due to the relativity is not always seen in this kind of astrometric observations, but with James James Webb telescope, it might change. We might need to provide the relativistic corrections to the Newtonian dynamics to explain the more precise observations. Okay? But so far, up till 10 years back, most of these astrometric binaries, most of them, we were able to predict and understand using Newtonian dynamics. Okay? So this is how the one of the very, very good examples of astrometric binary system works. And this is a scale, you can see it's given by in the terms of 5 arc seconds. So again, please understand that distances on the celestial sphere is measured in angles. Okay? And of course, this is an example of the two ellipses of the Sirius star binary system.